Hello and welcome. This is going to be our lecture video for April 10th. So go ahead, get out your notes. We've just got a little bit of notes to take, and then I'm going to be helping you on the worksheet I have linked on the calendar. All right, so let's revisit Pascal's triangle. Here I've started Pascal's triangle. It's very easy to make Pascal's triangle. You just start with a 1 on the top. You make these big diagonals of 1. It's ones, and then to fill in the interior, you're always adding the two numbers diagonally above a number. So let's see if we can add in another row here. So another 1 on the outside, and then a 6, 15, 20, 15, 6, 1. All right, now very important is how we refer to where we are in the triangle by rows and terms. And it's a little bit counterintuitive, but we call that very first one the 0th row. And then the next row, we call it the first row. And a handy trick for this is just you look at the second number. So we have filled in now to the 6th row. I can just look and see a 6 there and see that this is the 6th row. It really does make it easier to do it that way. It doesn't make as much sense at the top. But as you get farther down, this trick of just looking at the second number makes it really convenient to know where you are in the triangle. Now, this pattern also holds for the terms. And this one doesn't make as much sense, and sometimes we don't want to think of it this way. So this is one of the more confusing parts of binomial expansion, is that we call this the 0th term, and this the first term, and this would be the second, third, fourth, fifth, and sixth. And the reason for this is not as clear. It really helps us with one very specific type of problem, which is a combination problem. And we can use Pascal's triangle to solve these combination problems, and we're going to see a bunch of them in our next unit on probability, where if I'm rearranging objects and I've got 6 objects and I'm going to rearrange 2 of them, I just go to this 15 right here to figure out that I've got 15 different combinations, and there it's useful to call this the second term. That's about it. And that it's going to confuse us a little bit, because when we're doing binomial expansions, when it asks for the first term of the binomial expansion, we will go get this number 1 here. But if we want to plug it into our calculator, we've got to plug in a 0. So I'll explain that all right now with our notation for where we are in the triangle. So what we do when you are finding a number in the triangle, these numbers are called combinations. We do a big C, and then you put a number in front. It is a subscript and a subscript at the end, and that's an N and an R. And this tells you row number, and term number. So if I want to find a spot in the triangle, I can just say I want to go to 6C3. That means go to the 6th row, the 3rd term, that's a 20. So 6C3 is a 20. And I'll show you this is possible to plug into your calculator if you've got a scientific calculator or a graphing calculator. I'll show you where it is on the Texas Instrument. So if I wanted to do 6C3, for example, I type in a 6 and then go math over to probability down to 3. You see the NCR there. And then it fills in that 6. On some of the older calculators, it just has the 6, then the NCR. But this one, it actually fills it in nicely. So I want to do 6C3, and let's see if that is indeed 20. That's what we said it should be. All right, so you can go from 6 C0, so this should be a 1, the 0th term in the 6th row, it should be a 1, all the way up to 6C6, and that's the other 1 on the other side. So, one thing that is convenient about numbering the terms 0 through 6 is that this number here will never exceed this number. It can just go up to it. So we go from 0 to 6 to get the edges of the Pascal's triangle. All right, now there are a couple formulas with this that can be useful. I'm not going to have you memorize these, but I will have you add them to your notes. Let me just pause because I want to make sure I get them all. Okay, I've looked them up. So the ones I want you to know is that if you ever do any number C0, you're picking the 0th term in any row is always going to be a 1. So this is a formula. Anytime you see a 0 there, you know you're going to have a 1 over there. NCN, this gives you the 1 on the other side of Pascal's triangle. So this is another way to always get a 1. All right, NC1, the first term in the nth row is always n, right? So, because the first term is really the second number. So if I go down to the 10th row, the second number in the 10th row should be a 10. And last, if I ever go to n minus 1, I also get n. So this is the n on the other side. So you always have 1s in the boundaries, and then if you move one step in, you find n from both directions. Okay, I think that's all I want to say about combinations. Let's do now the generic expanded form of a plus b to the n. So a plus b to the n, it gets its coefficients from the nth row of Pascal's triangle. So the coefficients start NC0. And then the next coefficient is NC1. And the next coefficient is NC2, all the way up to NCN. So this is where we get our coefficients. All right, now our variables do kind of an interesting pattern. They start with a to the n, and then a to the n minus 1, and then a to the n minus 2, all the way down until there's no a's. So a to the 0th, which just goes away because that becomes a 1. And then the b's follow the exact opposite order. So this is our a variable. And I know this looks kind of messy when it's all just variables, but when we do practice with actual numbers, it makes a lot more sense. Okay, so for our b variable, it starts with no b's, b to the 0th, and then it goes b to the first, and then b to the second, all the way up to b to the n. So that's for our b variable. Okay, so if we put it all together into one line here, a plus b to the n equals nc0 a to the n b to the 0th plus nc1 a to the n minus 1 b plus nc2 a to the n minus 2 b squared plus dot 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 plus ncn a to the 0th b to the n. Okay, yes, I know that is a big mess right there. Let's try it with some numbers. So if I want to do let's do a plus b to the third. First thing I need to do is get my Pascal's triangle out, or I can just recreate it because I'm only going to the third row. All right, the coefficients come from the third row. All right, and then a, the exponents on a are going to count down from 3. So I've got my coefficients 1, 3, 3, 1. And then for my a variable, it's going to go a to the third, a squared, a, no a's. And then b is going to count up. So no b's, b, b squared, b cubed. Let me make these actually different color. And that is the expansion of a plus b cubed. We can get rid of these ones. I can write it a little bit neater. Make it a cubed plus 3a squared b plus 3ab squared plus b cubed. And that is the expanded form. All right, let's try some on the worksheet. So evaluate each expression, create the first 9 rows of Pascal's triangle below to help. All right, so I'm going to use the space, create the first 9 rows of Pascal's triangle. I'll pause the video to do that. All right, so I try to fit in the first 9 rows of Pascal's triangle, or Pascal's triangle to the 9th row. This is really the first 10 rows. All right, 7C3. So I go to the row with the 7, and I pick it's not the third number in, it's the third term, counting starting from 0. So 0, 1, 2, 3, I pick this 35 right here. So 7C3 is 35, and I'm just going to check that on my calculator real quick. So 7 NCR 3, and I do get a 35. 7C4, so that would be the number right next door. That's another 35. 8C4, so I go to the 8th row, the 4th term by starting at 0, so 0, 1, 2, 3, 4. Looks like a 70. You can get that one, you can get that one. I'll do 9C6 real quick. So it's really the 7th term in, so 1, 2, 3, 4, 5, 6, 7. It looks like an 84. Let me check that on my calculator. 9 NCR 6 does give me an 84. But I didn't write it out to 19 rows, so this is where I needed that formula. The 19th term in the 19th row should be a 1. And then the first term, but really remember that it's the second number, in the 15th row is going to be a 15. The second number, or the first term, because the first one's a 0, is always the row number. Here it's a 15. Okay. Let's try to expand one of these. We'll do one with a number. We'll do 10. So it's to the third, so I need to get my coefficients from the third row of Pascal's triangle. So I go 1, 3, 3, 1 with some space. And then I do 3, our a term, to the third. 3 squared. 3, no 3's, and then I count up with the m's. So no m's, m squared, m cubed. And on the ends, we should always see that exponent again. So this is 3 to the third, this is m to the third. All right, now we can simplify. 3 to the third times 1 is 27. Plus, that's going to be a 9 times 3, also a 27, but this time it's a 27m, plus 9m squared, plus m cubed, and then I kind of want to flip this around so that the m cubed is at the front. So m cubed plus 9m squared plus 27m plus 27. All right, let's try 12. 12 looks challenging. 3x plus y to the 4th. So I need the 4th row of Pascal's triangle. Its coefficients go 1, 4, 6, 4, 1. Now I count down with the a's. So 3x, all in parentheses, to the fourth. 3x cubed. 3x squared. Just a 3x. No 3x's. And then I count up with the b, which is here as a y. So no y's. Y. Y squared. Spacing all of our terms out with addition. Y cubed, and then y to the fourth. Okay, this looks a little messy. It's time to clean it up a little. One thing is that this 4 has to be distributed to this 3. So I need to know what 3 to the fourth is. I think that's 81. It is. So this here becomes an 81 x to the fourth, now with no parentheses. Plus this 3 gets distributed here. 3 to the third is 27 times 4 is 108. X cubed. This becomes a 3 squared 9 times 6 is 54, so plus 54. Oh, we're missing a y here. Plus 54, x squared, y squared. Plus nothing to distribute there, so this just becomes a 12 x y cubed plus y to the fourth. And there we go. 81 x to the fourth plus 108 x to the third y plus 54 x squared y squared plus 12 x y cubed plus y to the fourth. All right. Now for the rest of these, you just have to give a specific term. So here's where it gets a little confusing with Pascal's triangle, because the terms in an expression are not numbered starting from 0. The terms in Pascal's are numbered starting from 0. So we can kind of just ignore that for a second and just say the sixth term is the sixth number over in Pascal's triangle. So I need the sixth row of Pascal's. That goes 1, 6, let's see, 15, 20, 15, 6, 1. So the sixth term is going to be 1, 2, 3, 4, 5. We want this 6 here. So 6, and then by here, we're down to just a single a. So here I'll write it with an a, b to the fifth, and now I'm going to fill it in with an x and a negative 2. So 6 times x times negative 2 to the fifth. Negative 2 to the fifth. Make sure you do that negative 2 in parentheses. If you want to do that in your calculator, you get negative 32 times 6 is negative 192x. All right, let's do first term in this expansion. That's going to be your, since it's the first term, we know it's going to start with a 1. And it's going to be a to the 7th, no b's. And I'll just fill in this m here, so it's just m to the 7th. All right, let's try, let's just do the 3rd, 4th to the 7th. I guess we'll try 18, the 5th term of this expansion, and it's to the 4th, so we want the 4th row of Pascal's, which goes 1, 4, 6, 4, 1. The 5th term, we come all the way to this 1 at the end, and that's a 1, and then there's no b's at that point, or no a's, and b is counted up to 4, so this is 1b to the 4th. Then I just plug in the negative 1, so negative 1 to the 4th. Negative 1 to even powers always equals a positive 1. Let's check our work on 18. Yep, it is positive 1. That looks right, that looks right. Okay, we'll do number 20 now. So I need to know the 7th row of Pascal's triangle. So 1, 7, 21, 35, 35, 21, 7, 1. The 4th term, I want this 35 here. So I start with the 35, and now this was an a to the 7th, a to the 6th, a to the 5th, a to the 4th, so a to the 4th. And then this was no b's, b squared, b cubed. One thing is that these two exponents always add up to this exponent, so that's kind of a good way to double check. And now let's plug in x for a, so 35x to the fourth, and then 2 for b, 2 cubed. 2 cubed becomes an 8. 8 times 35 is 280. X to the fourth. So that is the fourth term in this all the way expanded. All right, we'll call it good there. Have a good rest of your day.